Okay. Thank you very much, everyone, for attending today. I think we are ready to start. So hopefully you all can see my screen. And now we are in the presenter mode or presentation mode. Okay, yeah, after a few days or a few lectures where we have covered the hardware, the microarchitecture, and an architecture of real-world processing in memory architectures, and we will also discuss a prototype for processing using memory and also a way of identifying and characterize data movement bottlenecks in real-world workloads. Today, we are going to talk about how to program processing in memory architectures. And the main focus of this lecture is going to be programming the PIM architecture. We are going to very briefly or very quickly recall what's the processing in memory architecture, what are the different components that it has, and then we are going to start talking about how to program it. So remember that the processing in memory architecture consists of multiple DDR4-like DIMMs that contain typically a number of 8 or 16 chips, and inside each of the chips we have multiple DRAM banks and also multiple small processing elements or small cores called DRAM processing units or DPUs. You may remember that, as I said, in each DIMM we have 8 or 16 chips, and this means that on each DIMM we have 1 or 2 ranks. And then if we take a look at the internals of a PIM chip, we will find 8 MRAM banks or DRAM banks that are called main RAM or MRAM, and the size of these banks is 64 megabytes. And we have also 8 DRAM processing units or DPUs. So in total, in one rank, we have 64 DPUs. If we look at the internals of the PIM chip and the DRAM processing unit, the first thing that we find in the PIM chip is a DDR4 interface for the host CPU to access the DRAM banks or MRAM banks, and also one control status interface for the host to communicate with the pipeline of the DPUs and send them commands to start the execution and also check when the execution of a kernel has been completed. So remember, inside each PIM chip, we have 8 of these 64 megabyte DRAM banks that are called MRAM, and we access these through some DMA engines that are also connected on the other side to a 24 kilobyte IRAM instruction memory and a 64 kilobyte WRAM or scratchpad memory for operands. And finally, we have here the DPU pipeline that consists of 14 stages, as you may remember. In the current generation of PIM systems, the DPUs run at a frequency of up to 350 megahertz, and this pipeline is fine-grained multi-threaded. It can execute up to 24 threads because it has 24 hardware contexts. And as you may remember, and I just said as well, there are 14 pipeline stages in this pipeline of the DPU, consisting of the dispatch stage that selects what the next thread to execute, the fetch stages to fetch the instruction from IRAM. We have some read operand stages to access operands in the register file, one format stage for operand formatting. Then we have 4 ALU stages to execute the instructions on the ALU, the different arithmetic or logic instructions, as well as accessing operands from the WRAM, and finally the resolve formatting or merge stages that we have at the end of the pipeline. Remember as well that the instruction set architecture of the DPUs is pretty rich. It's a 32-bit specific ISA, and it's scalar and in order, so it is designed for a scalar in order and multi-thread implementation. And even though it's a 32-bit ISA, it also supports compilation of 64-bit C code. So if you want to recall more about the UPMEM PIM architecture, the microarchitecture, and what are the different components, and what is as well the characterization that we did of all these different components, I would recommend you to check our previous lectures in meetings 2 and 3 about this architecture. And now we are going to start talking about the how to program this architecture, and to do so, we will start reminding what's the accelerator model, because this architecture, as you may remember, is based on this accelerator model. Let me know, guys, if there are any questions. In the meantime, I'm checking as well possible questions in the YouTube chat, so please don't hesitate to ask anything. I will check from time to time. Okay, so you may remember, and that's also something that we have briefly seen in the previous slides, that the UPMEM DIMMs coexist with conventional DIMMs. These conventional DIMMs represent the main memory of the central processor, and the integration of the UPMEM DIMMs in the system follows an accelerator model. In this accelerator model, the UPMEM DIMMs can be seen as a loosely coupled accelerator, and what this means is that before starting the execution on the UPMEM DPUs, we have to explicitly move input data from the main memory, from the memory of the host processor, to the memory of the accelerator, the MRAM banks, and then we have to explicitly launch the execution of the kernel on the UPMEM processors, on the DPUs, and finally we will have to fetch the results back from the MRAM banks to the main memory of the CPU. And remember that this is quite similar to the way that GPU computing operates as well, at least when we are working with discrete GPUs. And so you may remember that the first thing to do is to load for the SoC or the CPU, the host CPU, to load data that's going to be processed to the DRAM memory banks, and then transmit the corresponding command to the DRAM processors, to the DPUs, for them to start the execution, and then the execution of the kernel will start in the DPUs. So this is what we call here the data processing by the DRAM processors. And in the meantime, the central processor, the CPU, checks continuously whether the DRAM processors, whether the DPUs have finished the execution of the kernel. At that point, the memory bank on the DPU side, the MRAM banks, become again accessible to the SoC or to the host CPU for it to retrieve the results from the MRAM banks. So we are going to start talking about this part here, how to do the processing of data, how to perform the computation inside the DPUs. What we are also going to cover this part here, how to load input data to the DRAM bank, and also the last part, how to retrieve the results from the MRAM banks to the main memory of the CPU. So our first programming example is a very simple one, easily parallelizable, very regular computation that is called, that is the vector addition. As for sure all you know, vector addition is as simple as performing the element-wise addition of two input arrays. So we have two input arrays, A and B, and we add the elements from A and B one by one and store the results in an output array C. So the way that we are going to distribute the computation about on all the available DPUs in our system is by evenly partitioning these arrays in a way similar to what you see. So what we are going to do is assigning consecutive chunks of the input and the output arrays to the different DPUs. And then inside each of the DPUs, of course, we will have to load the corresponding chunks of the input arrays to the corresponding MRAM bank of, in this case, DPU 0 or DPU 1 and so on. But then inside each of the DPUs, we have to distribute these chunks of the workload among the software threads that run on the DPU. The name, or you might remember that the name of these software threads is tasklets. And in a very simple way, we can do the assignment, something like this. For example, imagine that we have only two tasklets running on DPU 0. So we will have tasklet 0 computing these elements of the output C and this tasklet one operating on these elements here. And that's going to be the same in all DPUs as well. We will typically use when we are using multiple DPUs to execute the same workload, we will typically use the same number of tasklets in each DPU. This is something that makes sense because this way the distribution of the workload it's going to be more regular. Okay, so before we continue, I would like to give you some general programming recommendations. These programming recommendations are publicly accessible. Let's say they come from the AppMem programming guide, from presentations and white papers from AppMem. And the first of these general programming recommendations is to execute on the DRAM processing units on the DPUs portions or parallel code that are as long as possible. This is something that makes perfect sense in a, give me 1 second. Yeah, so as I said, this is something that makes perfect sense in a parallel machine where we have multiple cores because we want to take advantage of the parallel processing power that these DPUs have, right? So if we have a thousand of DPUs in our system, the performance, the overall performance of our program is going to be faster if we are using more DPUs. So that's why it makes sense to run portions of parallel code that are as long as possible and also use as many DPUs in the system as we can. And also another important programming recommendation is to split the workload into independent data blocks so that the DPUs can operate on these data blocks independently. This is something pretty simple, pretty straightforward in the example that we have just seen in the vector addition, because as you have seen, we can evenly partition the input and the output arrays and assign these different partitions to the different DPUs, and they can operate in a completely independent manner. They don't need to synchronize in any way. They don't need to communicate in any way. And this is going for sure to ensure that we achieve the maximum possible performance, because as soon as we need to communicate across DPUs, we will have an extra overhead in this communication. And as you are going to see in later slides, this extra overhead is not negligible. The third programming recommendation is to use as many working DPUs as possible. This is something I mentioned before. If we have a system with multiple DPUs, we want to exploit as much parallelism as possible from our program. And the way of doing this is to use as many working DPUs as possible. And finally, the one last recommendation is to launch at least 11 tasklets or software threads per DPU. This is something that we already explained in one of our, actually it was in meeting 3, where we talk about the micro-benchmarking and characterization of the DPU architecture. You may remember that the arithmetic throughput of the DPU saturates at 11 tasklets for all data types and operations that we tested. Okay, so before we start the execution of a program on the DPU side, on the processing in memory side, we have to define how many DPUs we want to use in our program. So you might remember that a typical configuration on an AppMem-based PIM system is to have thousands of DPUs. So far, the most powerful AppMem-based PIM system can have 2,560 DPUs, and that's a lot of DPUs. You may not need so many DPUs at once. That will depend on what's the size of the input data or the data set that you need to process, right? So the first thing to do is to allocate the number of DPUs that we need. And the way of doing this is by using one API that is called DPU alloc, as you can see on the screen. And this DPU alloc creates one DPU set, which is the set of the DPUs that we are going to use in the execution of our program, right? So in this case, we are using DPU alloc to allocate a number of DPUs in this DPU set. So one question here is, can we allocate different DPU sets over the course of a program? And the answer is yes, we can. We can start a program, we can start running the program and maybe require 256 DPUs. And at some point, the intermediate data increases its size, and we have to use more DPUs, right? So it's possible to use more DPUs by allocating a new set with a larger amount of DPUs. By the way, when it comes to deallocating the DPU sets, we have to use this DPU free. But here you can see one example in this particular case is the Needleman-Wunsch algorithm, a bioinformatics algorithm used for sequence alignment. And the way that NW, Needleman-Wunsch, operates is by computing the anti-diagonals of a two-dimensional matrix. So as you know, the size of these anti-diagonals changes as we make progress. In each iteration, we compute one diagonal of the two-dimensional matrix, and the size of these diagonals is different in each iteration. So if we want to allocate enough DPUs for the size of the corresponding diagonal or anti-diagonal, we have to change the number of DPUs in the DPU set. So very first thing to do in the beginning of each iteration is to free the DPU set from the previous iteration, and then allocate as many DPUs as we need in the upcoming iteration. So after we have allocated the DPU set that we are going to use in the execution of our program, we have to load the corresponding binary, the program or the kernel that is going to run on the different DPUs. And the way of doing this is using another API that is called DPU load. And this DPU load loads a program that is stored somewhere, previously compiled this binary in this concrete path here. We load this binary onto the DPU set, as you can see, using the DPU load. So one question here is it possible to launch different kernels onto different DPUs at the same time? And the answer is that yes, it's possible. Why is that? Because we can allocate different DPU sets at the same time. You can allocate DPU set 1 and DPU set 2. I mean, one after the other, of course, in your host program, and then load two different programs, two different kernels on these two DPU sets. One good thing that this enables is that we can exploit task level parallelism, because we may have different tasks in the same program that can be executed in parallel. So what this means is that, for example, in the example that I was giving to you, one task is, or task 0 runs on the DPU set 0, and task 1 runs on the DPU set 1. And also, one other possibility is that we can have different programs or different processes using the UPMEM-based PIM system, because each of the processes can allocate its own DPU set, and they can run completely different things at the same time. So we know already how we have to allocate a DPU set, which is essentially defining what's the number of DPUs that we want to use in our program. This gives us an identifier of a DPU set, this DPU set here, and then we have to load the binary of the kernel, of the DPU kernel, onto the DPUs by using this DPU load. So next thing to do is to, right before starting the execution, right before launching the DPU kernel, what we have to do is moving the input data from the memory, from the main memory of the host CPU to the NRAM banks. Same as after the end of the execution, we'll have to retrieve the results from the NRAM banks to the main memory of the host CPU. So in order to do so, the UPMEM framework, the UPMEM SDK and runtime system provides data transfers to perform these communication. And these are what we call the CPU DPU transfers, when we move data, the input data typically from the main memory to the PIM enabled memory, and the DPU to CPU transfers when we move, for typically results, from the PIM enabled memory to the main memory. One thing that we are going to see now is what are the different types of transfers that we can make use of. So there are serial transfers. These serial CPU, DPU, or DPU, CPU transfers target a single DPU, a single NRAM bank. So if we use serial transfers to access multiple NRAM banks, the execution of these transfers happens sequentially, one by one. Another possibility is to use parallel CPU, DPU, and DPU, CPU transfers. In this case, we are targeting multiple DPUs, many MRAM banks at the same time. The only important consideration here is that the size of the buffers that we are transferring, let's say from the main memory of the CPU to the MRAM banks, should be the same size, and also exactly the same if it's the direction is the opposite, right? From the MRAM banks to the main memory of the CPU. And finally, we have a special case of parallel transfers that are the broadcast CPU DPU transfers. In this case, we are also targeting multiple DPUs, but we transfer a single buffer, the same data from the main memory of the CPU to the multiple MRAM banks. So guys, any questions so far? Okay. Okay, so let's start talking about the serial transfers. What's the way of doing these serial transfers? We have these two APIs, DPU copy to and DPU copy from. As you can imagine, these are to transfer to one DPU or from one DPU. So this DPU copy to copies from the main memory of the CPU to one MRAM bank. This DPU copy from performs the data movement in the opposite direction. So here you can see the actual code for these two transfers. In this case is DPU copy to. And one important thing to understand here is that we will typically use this DPU MRAM heap pointer name, that it's a pointer to the start of the MRAM range that can be freely accessible or freely accessed by application. So this is the address of the MRAM bank where the application can start allocating data that is going to be used by the DPU kernel. So we will typically use this heap pointer here in the DPU copy API. Then we also have some offset within MRAM. So starting from this MRAM address, what's the offset that we have to add to define what's the place where we start copying something to, and this is the pointer to main memory. And finally, this is the transfer size. So with these two instructions here, what we are doing is copying these two buffers pointed by either this pointer here or this other pointer here. The size of the buffers is given on this part of the on this input argument of the API, and the offset within MRAM where we are going to store these buffers is either 0 or is this number here, this amount here. So if you look carefully at these two instructions, what we are doing is copying one chunk of size, input size, DPU 8 bytes times size of T from this address in main memory to the beginning of the MRAM. That's what we do with the first instruction. And with the second instruction, we are copying a buffer of the same size from buffer B to somewhere in the MRAM that starts exactly where the previous buffer, the buffer A, finishes, right? That's why this offset here is equal to the size of the transfer size corresponding to buffer A. Okay, so for parallel transfers, this syntax is somehow different. In this case, instead of using a single instruction either to copy data from the MRAM, from the main memory to the MRAM bank or vice versa, here we first need to prepare the transfer and then we push them. So, and when we push them, we also define what's the direction of the transfer, either from the main memory to the PIM-enabled memory or the MRAM banks or the other way around. So here, first thing is to prepare, as you can see in this case for buffer A and buffer B. So with the DPU prepare xfer instruction, what we are doing is defining what's the pointer to main memory that we are going to use. So that's what we are doing here for buffer A and for buffer B. Then we define with this DPU push xfer API, we define what's the direction. In this case, is a data movement to the DPU memory, to the MRAM bank. We also have to define, same as we did in the serial transfers, what's the offset within MRAM and the transfer size. And finally, we have the broadcast transfers. They are only from CPU to DPU. And in this case, we transfer exactly the same buffer to all DPUs in the DPU set. As you can see, the syntax is pretty simple in this case, at least as compared to the parallel transfers. We need a pointer to the main memory. In this case, is this buffer A. We need to define the transfer size, and that's all. Because this whole transfer is this whole buffer is going to be copied to the MRAM of all the DPUs in this DPU set. So now one question is, when are we going to use parallel and serial transfers? Well, that will depend on the particular program that or a particular program or application, right? So as you can imagine, parallel transfers, because we can target multiple MRAM banks at the same time, they are going to they are going to achieve higher sustained bandwidth, right? So they are going to be faster, essentially, rather than using serial transfers that require targeting one by one MRAM bank. So they are going to be much slower. So in principle, we prefer to use parallel transfers. But the problem with the parallel transfers is that they are only possible when the size of the buffers that we are going to transfer, either to all MRAM banks or from the above MRAM banks, should be of the same size. So all these buffers should be of the same size. And in order for you to understand what I'm talking about, let me give you an example. This is one particular relational algebra operator, select, that we can implement on an admin-based PIM system. And in select, what we have is an input array where we want to filter, or we want to remove some of the input elements. In this case, we are going to remove the elements that fulfill this predicate true if it's even. So we are going to remove all even values in the input array. This way, we will obtain this output array. So when it comes to programming this and distributing this whole computation onto the available DPUs, what we are going to do is dividing the input array into different chunks of equal size, and we assign each of them to the different DPUs. Because the size of these chunks is exactly the same for all DPUs, so the buffers that we need to transfer from the main memory of the CPU to the MRAM banks of the DPUs are of the same size. So in this case, we can use parallel transfers. But now observe that the output depends on the values in the input array. And in this case, we have only 2 odd values. Here we have other 2 odd values, and here we only have 1. So what this means is that the size of the buffers that we need to return, that we need to retrieve from the MRAM banks to the main memory is not the same, right? So in this case, it's 2 elements, and 1 element. So in this case, we need to use serial transfers, unless we really know what's going to be the number generated by the number of elements in the output of DPU 0 and DPU 1. And in this case, we could at least use parallel transfers for these 2 chunks here, right? But yeah, I don't know if that's something that we are going to normally know in advance, right? So in the default case, we will have to use serial transfers. So we expect that these output transfers from the memory of the DPUs, the MRAM banks of the DPUs, to the main memory of the CPU will take longer because they cannot exploit as much bandwidth as the parallel transfers. But understanding well all these parallel and serial transfers is important, not only because we need to copy the input data from the main memory to the MRAM banks and then the results in the opposite direction. It's also important because using these transfers is going to be the only way of communicating across DPUs. The reason is that there is no direct communication channel between DPUs in the current admin-based PIM systems. And what this means is that every time that we want to move data from, let's say, one DPU in this PIM chip to another DPU in this other PIM chip, we will have to first copy the data from this DPU to the MRAM back to the main memory, and then from the main memory to the destination DPU. And that's something that we will see in some of the workloads that that we may want to implement on this system, right? And the typical example communication patterns can be, for example, the merging of partial results to obtain a final result. In this case, we need to use DPU-CPU transfers. So imagine that we are performing, for example, a parallel reduction or a histogram calculation, and we distribute the inputs across all the available DPUs in the system. And then when we are done, what we have in each of the DPUs is a partial result, a partial reduction or a partial histogram. And what we have to do is moving all these partial results from the PIM-enabled memory to the main memory for the host to merge the reduction results or the final or the partial histograms into the final result, right? And another possibility is to have to redistribute intermediate results for further computation. In this case, we will typically need DPU to CPU transfers and CPU to DPU transfers. Imagine, for example, an iterative algorithm, like graph processing. If we are following graph processing, for example, a top-down approach, we will generate kind of a frontier of nodes or vertices at the end of each iteration, right? And before starting the next iteration of the algorithm, we want to redistribute this frontier across the available DPUs, across the available workers and tasklets that we have in this PIM-enabled memory. So the way to go here is to copy the output frontier of one iteration to the main memory, have the CPU calculating how to redistribute this intermediate frontier, and then redistribute the frontier as the input frontier for the next iteration onto the available resources, the available DPUs in the system. So yeah, but as I said, it's important to understand how fast are these data transfers, because we are going to use them frequently, not only to communicate input data and output data between the CPU and the DPUs, but also for the inter-DPU communication. Do you guys have any questions so far? Okay, so how fast are these data transfers? We have studied this by using a micro benchmark. And in particular, we ran two different experiments. In the first experiment, we have used one single DPU. And what we did here was using a variable transfer size between the CPU and the DPU and from the DPU to the CPU. And in the second experiment, we target a whole rank of 64 DPUs and 64 MRAM banks. And in this case, we are transferring an array of size 32 megabytes. And we are going to change the number of DPUs that we use from 1 to 64. I'm not going to show you any results, any data transfer results for more than one rank, but I can tell you that in preliminary experiments, I have observed channel level parallelism. So if your system has multiple DPUs, and these different DPUs and the corresponding abment DIMMs are connected to different channels from memory controllers of the host CPU, you will be able to exploit channel level parallelism, and this way achieve a higher bandwidth than the bandwidth that you're going to observe for a single rank here in the experiments I'm going to show you. One thing to tell you upfront is that the maximum bandwidth is going to be bound by the maximum bandwidth, theoretical bandwidth of DDR4 memory, which is typically around 19 gigabytes per second per DRAM rank. And as you can imagine, this is not a high bandwidth, right? It's exactly the same problem that we usually have in processor-centric systems, is the fact that we need to access all the data from DRAM, and these we can do it at a limited bandwidth, right? So this is the reason why or one of the reasons why we want to amortize the cost of the data transfer. So we have to move data from the main memory of the CPU to the MRAM banks, and that's something that we can do taking advantage of the DDR4 bandwidth, because the admin DIMMs are connected to conventional memory channels, and in order to amortize these data transfers that are, let's say, relatively slow, at least compared to the fast execution that we can have inside the DPUs. That's why we want to have as large pieces of code executing on the DPUs as possible, because this way we can amortize the overhead of the data transfers. So let's first take a look at the results for a single DPU. In this case, I'm showing you here the sustained CPU, DPU, or DPU, CPU bandwidth for different transfer sizes from 8 bytes to 32 megabytes. And one thing that we observe for both CPU, DPU, and DPU, CPU transfers is that there is an increase in the sustained bandwidth as we increase the data transfer size, and at some point the bandwidth starts saturating. So key observation here is that we want to maximize this bandwidth, right? So, and the way of maximizing this bandwidth is using as large data transfers as possible, because this way we will achieve the highest possible sustained bandwidth. Now, if we take a look at the results for one rank, here we include serial, parallel, and broadcast CPU, DPU transfers, and serial and parallel DPU, CPU transfers. And here we have a fixed size for the input array for the transfer size, but we changed the number of DPUs from 1 to 64, as you can see on the slide. So these are the results for the serial transfers. These are CPU, DPU, and these are DPU, CPU transfers. The bandwidth is completely flat, as you can see. And the reason is that we are executing the transfers sequentially, right? So with each of the transfers, we target a single MRAM bank. So if we, instead of transferring to a single MRAM bank, we transfer to 64 MRAM banks, we will have to do them one by one. So in the end, we are not exploiting more parallelism. We are transferring more data to more MRAM banks, employing more time. And that's why the bandwidth is essentially flat for the serial transfers. For the parallel transfers, we observe that the bandwidth increases as we increase the number of DPUs, and that's good. So that's why we want to exploit the parallel transfers as much as possible, because we will be able to enjoy more sustained bandwidth. There is one observation here, is that the bandwidth of the DPU CPU transfers is slightly higher, is a little bit higher than the bandwidth of the DPU CPU transfers, and the reason is that is the way that these transfers are implemented in the PIM runtime library. And also different is the implementation as well of the broadcast CPU DPU transfers. In this case, we are achieving the highest bandwidth in this case, and the reason that we observe is that there is higher temporal locality in the CPU cache hierarchy, because we are transferring the same buffer to all MRAM or involved MRAM banks, right? And it's likely that this whole buffer fits in the CPU cache hierarchy, or at least some parts of it. Also, an interesting observation here is that the peak bandwidth that we achieve for 64 of the DPUs, 64 DPUs in the same rank, is almost 17 gigabytes per second, which is actually quite close to the theoretical peak bandwidth of DDR4 memories. As I said before, 19 gigabytes per second. And if we cannot achieve this peak bandwidth, or one of the reasons why we likely cannot achieve this peak bandwidth, is because the runtime system, the PIM runtime, needs to perform a transposition when copying the data from the main memory to the main memory CPU to the MRAM banks. And the reason for that is that the way that the DPUs need the data to be laid out is different from the conventional way that we lay out data when it's going to be accessed by only the CPU memory in the main memory. So by only the CPU, what we normally see in the main memory of the CPU. As you may know, the typical way of storing 64-bit words in DRAM is by storing them horizontally. And if we have 8 chips in one rank, we will typically assign 8 consecutive bits to the 8 consecutive chips, as in a similar way as we can see here on the screen. But when it comes to operating on this data by the DPUs, we need the DPUs to see full 64-bit words. Why is that? Because we want each DPU to be able to operate on a whole word, right, on a whole element of our input array. And these elements should be, or the UpMem system supports up to 64-bit elements, right? So what the runtime library needs to do is transposing in some way these words that are horizontally laid out in the main memory of the CPU, transposing them in a way that entire 64 words go to the same DRAM chip, and this way can be operated on by the corresponding DPU in this chip, or one of the corresponding DPUs in this chip. Okay, so if you want to experiment yourself with these micro benchmarks, you can freely access them from our repository, where you will find all the micro benchmarks for CPU, DPU, and DPU CPU transfers. Now we know how we can copy data from the main memory of the CPU to the MRAM banks and vice versa. So we are ready to, and by the way, remember that we also know how to allocate a DPU set and how to load a program, a kernel, onto the DPU set, onto the different DPUs in the DPU set. So now it's time to launch the kernel and start the execution on the DPUs, right? And to do so, we use this DPU launch that launches a kernel on a DPU set. So as you see, this DPU launch, the only thing that we have to we need to indicate to this DPU launch is what's the DPU set that we are targeting. And the program that we loaded previously on the IRAMs, on the instruction memories of the DPUs of this DPU set, will start the execution. Another parameter that we pass to this DPU launch API is a parameter that defines whether the execution of the kernel is synchronous or asynchronous. The main difference between these two is that in the first case, the execution of the application on the CPU gets suspended until the kernel finishes on the DPU side, and at that point, the CPU can continue the execution, whatever CPU instructions, whatever host instructions we have after this DPU launch will be executed after the kernel has finished on the DPU side. Or we can do this asynchronous execution where the kernel is launched and then the CPU is free and can continue performing other operations in the same program. What do these asynchronous execution enable? So some ideas is that, for example, we can exploit task level parallelism because we can have concurrent execution of different kernels on different DPU sets. Imagine that we have two different DPU sets in our program. If we use so we have two different DPU sets in our program. We load two different kernels on these two different DPU sets. We start the execution of the program by the host thread, by the main thread that runs on the host CPU. And at some point, we reach this DPU launch. If this DPU launch for DPU set 0, right? If this DPU launch is synchronous, the CPU will stall until the whole kernel is done. And then it will continue and it can launch the next kernel onto the other DPU set 1. That's one possibility. There we are not exploiting task level parallelism. We are simply executing first one task on DPU set 0, and then another task on DPU set 1. But if we use the asynchronous execution, we could do this DPU launch on DPU 0, do it asynchronously. This way, the CPU is free and can launch the second kernel on DPU set 1, and this way enable the concurrent execution of both kernels on different DPU sets. And another thing that we could do is enabling concurrent heterogeneous computation on CPU and DPUs. So we can have the CPU launching one kernel on DPU set 0, and then the CPU is free. If the launch was asynchronous, the CPU is free and can continue execution and can operate on different parts of the input data, for example. And this way we have this concurrent heterogeneous computation. Okay, one last thing with respect to executing the kernels on the DPU side is how to pass the input parameters to the kernel. So because as you may have seen, this DPU launch doesn't have any input parameters, any input arguments for the kernel. Well, in this case, we again use either serial or parallel transfers, but in this case, instead of transferring from the main memory to the MRAM bank, we transfer directly to the WRAM, to the scratchpad memory. And so these input parameters and also some results can be kept there in the WRAM for the DPUs to use them, or for the host CPU to retrieve them. The way to declare these input arguments or these results that we want to transfer, we want to retrieve via this WRAM is by using this host qualifier that indicates, and this is, by the way, something that we declare in the task.c file where we have the DPU kernel that is going to run on the DPUs. So the way of declaring these input arguments or results is by using this host qualifier, as you can see. And then in the host code, the code that runs on the CPU, we use these, in this case, these either DPU copy to, or we use parallel transfers with the corresponding DPU prepare xfer and DPU push xfer. The only thing is that in this case, instead of using this pointer to MRAM, to the MRAM heap that we defined before, we use directly this identifier of this array or this memory structures that reside in the WRAM. Okay, recall our vector addition example. We have these input arrays A and B and one output array C. We partition them evenly and distribute them onto the DPUs and the tasklets. Now, how does the kernel that we execute on the DPUs look, right? How does this kernel look? If you check this code at first sight, you will see that it's not very complicated. This is essentially C code with some extensions or some library calls, like, for example, this me that defines what's the tasklet that is executing this code. This way we can use one tasklet ID to be able to address the data that we need to access from MRAM, or to store the results in the corresponding place in MRAM. We define as well here what's the size of the vector tile that is processed by a DPU. Remember that this is one of the input parameters that we have transferred before by using one serial or parallel data transfer, and we are storing this in this variable. Here we have the MRAM addresses of arrays A and B. These are the two input arrays of the vector addition. Remember, and you have already seen that array A, or the part of array A that is going to be computed by this particular DPU is stored here in the MRAM heap pointer, in the address pointed by the MRAM heap pointer, and then this is the corresponding address for array B. Here we need to do some WRAM allocation, and we do that using this memalloc. Memalloc allows us to allocate in WRAM an array of a certain size. In this case, the size is block size, because this is the size of the chunks that we are going to copy from the MRAM to the WRAM for the later execution of the vector addition in WRAM. And these are the MRAM WRAM transfers. As you see, we are transferring from this MRAM base address of A and MRAM base address of B to this cache A and cache B that we have previously allocated in WRAM, right? So what we are essentially doing here is bringing one, so in each of the iterations of this outer for loop, what we are doing first of all is transferring one chunk of a certain size, let's say block size, from MRAM to WRAM for array A, and from MRAM to WRAM for array B, and then we can perform the vector addition. We are going to see the code in the next slide. And finally, when we have the vector addition performed for these two chunks that we previously copied to the WRAM, we can return the final result that is now in WRAM in this cache B. We copy it to the corresponding address in the MRAM that is pointed by this MRAM base address B. And here in this slide, you have the simple inner loop of the vector addition that is executed by a single tasklet after bringing one of these chunks of A and one of these chunks of B to the WRAM. The corresponding tasklet performs this element-wise addition, as you see in this inner loop. So a tasklet, as you know, is a software abstraction of a hardware thread. So it's the software thread that runs on the DPU by using one of the hardware contexts that the DPU has. And each tasklet can have its own memory space in WRAM. We have just seen that. We have just seen how to allocate a buffer A or buffer B in the WRAM using this memalloc instruction. And also, well, tasklets can also share data in WRAM by sharing pointers, because the WRAM is a single WRAM for the whole DPU. So in the end, there are ways for one tasklet to share pointers with other tasklets so that they can operate on the same data and they can access the same data in WRAM. This is something that makes sense to do if it's, for example, only input data that is not going to be modified. If it's going to be modified, if it's output data or data that or memory locations in WRAM that we need to write, we need to have a way of synchronizing the tasklets within the same DPU, such that we avoid, for example, data races. So probably most of you are familiar with mutual exclusion. Here, what we essentially do is defining a critical section that can only be accessed by one tasklet that acquires one lock. And after acquiring this lock, this tasklet can execute the critical section, and then it releases the lock by using this mutex unlock, right? And after that, another tasklet can acquire the lock and execute the critical section and then release it and so on. So this is a well-known way of synchronizing different threads in a parallel programming. Handshakes are also very typical. In this case, there are only two tasklets involved. One of them is waiting, the other one is calculating some partial result that is going to be transferred to the tasklet that is waiting. So these are the handshakes. We can also have barriers to synchronize all threads that are executing on the DPU or tasklets executing on the DPU. And we can also have semaphores. So we are going to see today one example, in this case, how to use the barriers. And the way, we are going to explain it by one interesting example, that is the parallel reduction. In parallel reduction, what we need to do is the goal of parallel reduction is to obtain a single value from all the values that compose an input array. The actual value can be calculated in different ways. For example, we can obtain the maximum of all these elements, or we can obtain the minimum of all these elements, or we can obtain the sum of all these elements. And this is the case that we are going to target here. The parallel sum reduction of all the elements of an input array into a final reduction sum. So what we do here is, again, if we have multiple DPUs, we distribute the whole input array across the multiple DPUs. In this case, for now, we are going to assume that there is a single DPU. So we distribute the chunk that has been assigned to this DPU across the tasklets that we have running on this DPU. And in this case, we assume 4 tasklets from tasklet 0 to tasklet 3. So how can we compute this parallel reduction if we have 4 tasklets? Well, so the way to go is to first calculate a local sum by each tasklet. So this part of the input array is assigned to tasklet 0. So tasklet 0 goes one by one over all these elements here and accumulates them on some variable that represents the local sum. Tasklet 1 is going to do the same, tasklet 2 and tasklet 3. And at some point, when we have all these local sums, we will reduce them as well, right? So these, as you see, is a two-step process. We first generate the local sums, and then we reduce the local sums into a final global sum. So how do we implement these on a kernel for a tasklet to execute this kernel? Well, we can have a for loop for each of the tasklets. For the tasklet to go over all the elements of the chunk that has been assigned to it. This chunk has a certain size, and the first thing to do, same as we did for the vector addition, is to copy from MRAM to WRAM to this cache A that we have previously allocated in the cache, and then we do this reduction. Essentially, it's like reading one by one all the elements of that we have in this cache A array. We read all the elements one by one, and we accumulate them in a local count. So that's what we do here, accumulate the local sum. And when we are done with this for loop here, we will store the local sum of each individual tasklet in some memory location, shared memory location in WRAM. That is, as you see, identified by the corresponding tasklet ID. So this message is another array with as many elements as tasklets we are running on this DPU. And as soon as one DPU finishes with its own reduction, with its own local sum, we store the local sum in this corresponding position of message. So now, imagine in the previous slide, we had 4 tasklets. Now we have 4 of these partial sums. So one way to go is to simply use a barrier here to make sure that all 4 tasklets are done with this first part, this first step of the parallel reduction. Then we synchronize here, which means that all threads or tasklets wait here in the barrier for the other tasklets to arrive at this synchronization point before we continue the execution. And in this case, the second step is executed by a single tasklet. So one of the 4 tasklets is going to read the corresponding elements that have been, the corresponding local sums that have been stored in this message array, and it reduces them sequentially, and finally store the total sum, the final sum, into some element for the output, right? That is going to be retrieved by the CPU. But this is one way of implementing this. Observe that we are exploiting parallelism in the first step because we have multiple tasklets operating on different parts of the input array and calculating local sums. And then we need to synchronize all the tasklets to make sure that all the local sums have been generated. And then finally, we have a single tasklet. So we are not exploiting parallelism anymore here. Even though we may have, I don't know, 16 tasklets, and we may have a few of these partial local sums here, we are only using a single tasklet in this implementation. Another possibility is to use what we call the tree-based reduction. This is a slide from or other PNS on the heterogeneous system. This is to explain GPU implementation of parallel reduction, but in the end, we are going to do something quite similar here. The proposal is to implement a tree-based reduction. In the tree-based reduction, we can we will have a lower number of iterations. In total, if we need to reduce n elements, we can do it in log n iterations. And essentially what happens here is that in each iteration of this tree-based reduction, half of the threads or the tasklets in the case of the DPUs retire, and they continue the execution until we obtain the final sum here. So we can do something similar, like a tree-based reduction inside the DPU for the second step. After this barrier, remember that before this barrier, we have the calculation of the local sum for each individual tasklet. So here we set this barrier, and we have this for loop that in this case is using all the available tasklets. And what we are doing, same as we have seen in the previous slide, is that we assign two of the local sums that were previously stored in this message array. We assign them to one particular tasklet. This tasklet adds them and store them back in the message array. And after iteration, half of the tasklets will retire until we have a single tasklet only in the last iteration of this for loop, and this single tasklet obtains the final sum and stores it in the corresponding output location. And one observation, one thing that you have to observe here is that at the end of these each of these iterations of the tree-based reduction, we need again to synchronize, same as we did before starting the tree-based reduction, to make sure that all tasklets have stored the corresponding result or partial result in the message array. This is another way of implementing the tree-based reduction, and it's possible to implement the tree-based reduction as well as using handshakes. If you want to see a comparison of these three different implementations, I would recommend you to check the appendix of this paper. And if you want to learn more about parallel reduction, I mentioned or other PNS processing and projects and seminar course on heterogeneous systems, where we are teaching GPU programming, and there we also had a lecture about the parallel reduction. That is a pretty interesting pattern, I believe. Okay, so we will continue talking about programming the PIM system in later lectures, and also other processing in memory systems. But for now, I would like to recommend you to take a look at our benchmark suite called PIM benchmarks. This is a set of workloads that can be used for sure to evaluate processing in memory architectures like the PIM-based processing in memory architecture, but it can also be used as templates for programmers with different programming patterns implemented for the DPUs and the multiple tasklets. So in total, this PIM benchmark suite contains 16 different benchmarks out of 14 different workloads. And these are workloads that we selected because they are memory bound. They show to be memory bound in conventional processor-centric systems like CPUs or GPUs as well. Here you can see a whole list of these benchmark suite, benchmarks coming from different domains like dense and sparse linear algebra, graph processing, neural networks, image processing, etc. And these are the different benchmarks and the acronyms that we use for them. We are going to see an evaluation of these PIM benchmarks on the real PIM-based PIM systems, but that's something that we will do in a later lecture. What I want to show you today is that all these workloads are memory bound in a conventional processor-centric system. We use the roofline model to characterize these workloads on a CPU, and as you can see, all the workloads fall in the memory bound area of the roofline. And also these workloads are very diverse. Observe that today we have talked about, for example, different ways of communicating tasklets inside the same DPU, or we have talked also about different ways of communicating across DPUs as well. So all these patterns are present in the PRIM benchmark suite. So we have many we have different memory access patterns like sequential, strided, random. We also have different types of operations and data types for the different benchmarks and different communication and synchronization needs. And regarding the communication and synchronization, as you can see on this table, that some of them use handshakes, barriers, mutexes, and also you can see that we have cases with inter-DPU synchronization where we require result merging or where we require redistribution of intermediate results. I mentioned before, for example, when we talk about the redistribution of intermediate results, I mentioned graph processing algorithms. So here we have, for example, the BFS algorithm, which is an important graph processing workload. And we are going to see an analysis of more detailed analysis of these workloads and how they perform on an UpMem-based PIM system in a later lecture. But if you want to access them and start experimenting with them, you don't even need to have access to a real system. You can just download the SDK from the UpMem website, and the SDK comes with a simulator, and you can start running all these workloads on the simulator and see how they perform. The simulator will provide you some can provide you some estimation of the execution time and some measurement of the execution cycles as well. So yeah, this can allow you to understand more about the processing in memory architecture and how are workload characteristics that make them suitable for the particular PIM system. And as I said, in a later lecture, we are going to talk more about programming this UpMem PIM architecture and also other processing in memory architectures. And we will also discuss the evaluation of these PRIM benchmarks on the real UpMem-based PIM systems. And also we will identify what are the characteristics that make a workload suitable for this UpMem-based PIM system. So this is all from my side today. I don't know, guys, if you have any questions. If you have them, please go ahead and ask. I don't see any questions in YouTube, so I guess that if you guys don't have any questions, we will be done for today. Okay, if there is nothing now, you know that you can reach out to me later, send me an email or ping me in any way, and I will be glad to answer any questions that you may have related to this lecture or previous lectures as well.